previous section, but here I am. And I'm going to speak today about a little project that we've got, we've just got up and running, where we're focusing on regional ecosystem monitoring to improve understanding of oyster productivity. So this project is funded by Natural Resources Eyre Peninsula through an ADAPT NRM grant, and also Oysters South Australia. And it really came about because South Australian oyster growers wanted to get a better understanding of the impact of these changing environmental conditions on oyster health and productivity. So we're talking about growth, conditioning and mortality, and there's really very little information about that for South Australian growing regions, or any information that there is hasn't really been interrogated in any detail to draw down and relate it to productivity. And it's all about promoting industry resilience in the face of any potential future changes that might occur in environment or in relation to climate or that sort of thing. So we're focusing on water quality, changes in water quality and changes in food web dynamics, but it's great because it also gives us an opportunity to focus a bit on what is really the elephant in the room for the oyster industry, and that's ocean acidification. And I'll get into that a bit further in a few more slides. So speaking about food webs first, here we have our highly simplified marine food web, where we're going from the phytoplankton, the photosynthesizers are taking in the light and nutrients and forming the carbohydrates or the compounds that feed up the rest of the food web to our charismatic marine predators. This was really I guess the conventional wisdom on the way things went for oysters. They basically ate phytoplankton. It wasn't until I was at a presentation with the industry where they went through the long-term phytoplankton data set that South Australian Shellfish Quality Assurance Program has collected, and started to look into that and say, okay, at this times of the year you've got lots of food, lots of phytoplankton, and then this times of the year you've got none. And a few of the growers started to say, well, hang on a sec, why am I getting really good conditioning when there's no food? And obviously that's because there's quite a bit more that's going on in the ecosystem that could be available to oysters for food. Particularly all this small stuff which incorporates viruses and bacteria, picophytoplankton, microzooplankton and so on and so forth. So if we think about this in another way, the type of food webs that we're likely to be finding out in the ecosystem. And this figure is delineated here along the 2 micrometre diameter size. We've got increasing phytoplankton size across the top. So on the right here first is what would be termed the classic food web, based upon large diatoms and dinoflagellates being fed through the zooplankton to the higher trophic levels, in this case oysters, or being eaten directly by the oysters. So this may also be small pelagic fish, let's say, who are then passing this productivity on to the high trophic levels. This is the type of food web you find in areas where there's a lot of nutrient enrichment, and based on nitrate as a nitrogen source. Now on the left here, we've got what's known as the microbial food web. It's underpinned by the picophytoplankton, very, very small phytoplankton, types of phytoplankton. They can get down to less than a micron in diameter. And you can see there's a lot more steps in here. This would be our incorporate our bacteria and viruses. We've got our sort of microzooplankton here before we get to the zooplankton and the oysters or the fish. And the prevailing wisdom with this is, with each step in the food web, you lose a bit of energy because that organism needs to use some of that energy to survive itself. So more steps means a less efficient transfer of the energy through to the oysters, and perhaps these components of this food web might be of less nutritional value to the oysters. So changes in the food web will change the size and the type of food that's available to oysters, and possibly the nutritional value of that food. And we want to understand what the drivers and timing are of changes in the food web dynamics, and as I've just mentioned, it typically involves changes in nutrients. So as I said, this is what you find generally if you've got lots of nitrate around. Nitrate can be stored, so large phytoplankton with large vacuoles can take up more than they need. and quickly outcompete the smaller phytoplankton. Now, on the other hand, ammonium can't be stored, and the organism that's going to dominate when ammonium is the source of nitrogen will be the one that can take it up and use it the quickest. It very quickly diffuses across membranes. Typically that's going to be the really small things with small surface area to volume ratios. So if we've got lots of ammonium around, we'd be expecting this to be happening, this to be the food web, and if we've got lots of nitrate, we'd expect this. Now, moving on to acidification. Why is this potentially a problem? It's a problem because the acidified waters impede calcification. So this can affect reproduction, but more so shell formation of the oysters, and it's mainly an issue for larvae and spat when they're very small. And it's been a major issue in the US Pacific Northwest. Between 2005 and 2009, they had a really big problem. They were getting greater than 70%, greater than 80% mortality of their oyster seed due to the upboiling of acidified water. And they were staring down the collapse of an industry, $110 million a year, 3,000 jobs. This is when, as it usually happens, the US federal government decided they have to put some money towards it, so they put in $500,000 for ongoing monitoring, which has allowed them to develop mitigation strategies. So they can do things now like, well, they buffer their hatchery tanks, but they can also observe changes in pH and think about when they want to take in the water that they're going to put in their hatchery tanks. And it's really a great thing on part of the oyster industry that they've got a desire to get ahead of the curve, so to speak. So these South Australian oyster industries are already wanting to think about this sort of thing, recognising that foresight is better, and they're wanting to start thinking about ways that we might be able to mitigate this. And the first step in this, obviously, is beginning to collect the observations to see if we're seeing any change, which is where this project comes in. So how are we going to do this? We will be focusing to start with on the Coffin Bay region, and we're deploying 2 environmental probes in 2 growing areas, one in Coffin Bay, one in Kelladie Bay. These probes will be attached to data loggers and will have telemetry, so we'll be able to look at the data on the web as it's being collected. We'll be getting continuous water quality data, temperature, conductivity or salinity, pH, dissolved oxygen and fluorescence. And we'll be ground truthing this data, which is very important, and augmenting it, I guess, by going out and doing seasonal sampling to collect nutrient information on the nutrients so that we can explain what we're seeing while we're out there. We'll be getting pigment data, size fractionated pigment data, so that we can see what's happening in the different sizes of the phytoplankton community. Information about microbes and plankton, so viruses, bacteria, picophytoplankton, phytoplankton, microzooplankton and mesozooplankton. And also inorganic and organic matter and total suspended solids, because one of the things that I didn't have in that food web was detritus, which may also be something that the oysters are feeding on. And we've got it closely, we'll be getting additional information from a closely related project, or we'll be working very closely with the guys that are on this project as well. It's the FRDC oyster feeding project. It's being run by Xiaoshu Li out of Sadi. And this is very important for this project because part of it, that's where the examination of oyster conditioning will come in and how that varies across time. But also, very importantly, Xiaoshu and his team are going to find out exactly what they're eating and what the nutritional value of those things is. And we can then, once we know that, we can then go out and focus on, or in future, we'll be able to focus on monitoring the things that are important. We'll also be putting this, using other data streams to put the data we get from this project into a more of a regional context. First up, we've got the same IMOS data, which is being collected. There's a mooring out here off York Peninsula and a mooring out here off Kangaroo Island. This is actually the national reference, part of the National Reference Station network. So data from here we can compare to the other, or is collected in the same way, analysed in the same way as data from the other reference stations around the country. So it'll give us a national context as well to what we're finding out. There's also CTE transects that run through here out to the edge of the shelf. And we collect basically the same information as we'll be collecting on our seasonal sampling events. So we can see what's going on out in the wider region, particularly in our upwelling area, and what that means to Coffin Bay. There's also out here off Kangaroo Island the IMOS PCO2 mooring, which is collecting a lot of information on ocean acidification. That's been out there, well, it's been operating since at least 2010. And as part of the IMOS sampling, we collect information on alkalinity. Another one that we may be able to get data from is occurring up here in Boston Bay. It's the Aquaculture Environmental Monitoring Program that will be running for the next 4 years. There's sampling twice a year, I believe, for similar information to what we've got here. And it's important to understand what's going on out here because this is our upwelling area. So during the upwelling season, November to around April, we get the upwelling coming off the shelf up here, and it blankets the shelf in a bottom layer around here, and it gets brought to the surface when we get these southeasterly blows off KI and off Coffin Bay up here. And it's not constant southeasterlies through the season, as we probably know. You'll get that interspersed with southwesterlies. So what happens is it comes to the surface up here, it starts to get pushed around with the southeasterlies and the prevailing circulation. When you get a break in that, you get a southeasterly blow and it can be blown into Coffin Bay. So you can get enrichment happening in Coffin Bay, but you can also get problems because some of those dinoflagellates or the diatoms may be harmful algae. You can get harmful algae getting blown into Coffin Bay as well. So we need to keep an eye on what's happening out and put things in a regional context too. 2 minutes, okay, well, we'll skip that one. Get straight to outcomes. What are we hoping to achieve from this? What we'll be getting, first and foremost, I guess, is a baseline understanding of environmental variation in Coffin Bay. It'll give us a deeper understanding of the health and dynamics of the local marine ecosystems. So, aiding in maintenance and improvement of regional water quality, because we'll be able to monitor it with these probes, understand when the changes are happening, maybe think about why they're happening, and through that assist in the development of stormwater management plans. But most importantly, it's going to promote the ecologically sustainable development of the oyster industry through assisting in the development of evidence-based decision-making frameworks for management and aiding in the development of plans to help industry adapt to future change, whether it's climatic or anthropogenic. And those long-term IMOS data sets are going to help us look at what's happening in climatic terms, potentially, and put our data into that sort of a context. And another sort of bonus, I guess, from this project will be that it could lead to the development, or it will eventually lead to the development of coupled hydrodynamic phylogeochemical model for the region. For an example here, this is work that was done by Henry Ellis with Jochen Camp for his honours. Henry's now doing a PhD with us in the oceanography group at SARDI. So he developed a hydrodynamic model for Coffin Bay. Back here we can see this is Coffin Bay and Kelladine Bay down here. And he's found that it's a tidally dominated system, small-scale seasonal density-driven outflows. Some areas experiencing high water ages due to a lack of tidal mixing. So that's important also for trying to explain what we're seeing out here in terms of ecosystem change. This model, we are now further extending this and refining it with another colleague at SARDI, Anna Redondo, because Henry's moved on to work on Gulf St Vincent. And the information that we're getting from these probes and from this ongoing program will give us all the data we need to develop this biogeochemical model, similar to the one that we've already developed for Spencer Gulf, which we couple with the hydrodynamic model and provide another really important and valuable tool for managing this region. So the hope is that, I'll move on to acknowledgements now, the hope is that we'll eventually be able to find the funds to extend this to other growing regions, because each growing region is obviously going to be different. It's going to have different influences, different changes in the environment. But we'll have to see how we go with that. And I'd like to single out here, obviously, Oyster Growers Association and the Oyster Research Council, but also Ben Smith Natural Resources Eyre Peninsula, who was instrumental in getting the probes. And this is Xiao Shu's team, Sean Henderson and Ida, who are the PhD students working on his side of things that are doing most of the sampling for us when they go out and do their sampling. Thank you.
Okay, I think we've got time for one or two quick questions.
Have you taken into account freshwater inflows, groundwater inflows into, say, Kelly Bay?
That's something that we'll definitely be looking for and looking into, and hopefully, that'll come out as part of. We've just started this, I should have mentioned, so we haven't really got any data to talk about as yet. And yeah, all of those sorts of influence will be considered, and that's hopefully the sort of things that we're going to pick up in all the data that comes in. We're having minor issues at the moment with the probes. More so in terms of the fact that the company has been taken over, and we're just trying to let them get through that transitional phase before we can get someone to come out and sort them out. But certainly there'll be CTDs dropped as well when we do our sampling. So we'll be looking out for all of that sort of stuff.
Any more questions?
What's the timeframe?
So with this minor delay that we're having in getting these probes sorted out, it'll be running for 2 years and hopefully finishing mid-2017, I think, is what we're aiming for with the delay. And again, if we get further funding, well, the probes will be there. The probes are there and they'll stay there. But we're looking at pursuing funding from elsewhere to get probes in different growing areas and extending the sampling to different growing areas. And certainly that's what the growers are keen for, but we have to see what we get from this first to be able to push that.